My talk is titled Visualizations and Graph Theory and the Wolfram Language. It's a mouthful. So my name is Michael Sollami. Thank you for coming. I'm here from Cambridge, Massachusetts. So I work at a computer vision startup. What's that? Zoom? I can't zoom. Look harder. It's called Ditto Labs. So basically, we do turnkey, cloud-deployed computer vision as a service APIs. And there we are, right next to Massachusetts Institute of Technology. I'm going to talk a little bit about Ditto at the end. But just a shameless plug, I'll be giving out API keys after the talk. So if you're interested in computer vision, just come talk to me. So what I'm really here to talk to you about is a bit of graph theory, and then mostly about visualization. And so I want to start with a big question. What is the future of scientific and educational communication? So how can we build a new world of interactive educational apps? What further medium can we imagine? Where does Mathematica fit in? What would the archive look like in 2025? These are interesting questions, and the incomparable Brett Victor answered them, at least in part for parts of graph theory, in about 5 years ago by rewriting, or rather redesigning, an academic paper as an interactive document of sequential art. So what does that look like? It looks like this. So he rewrote Watson-Strogatz's Nature paper on network theory, and he added a small amount of lightweight interactivity in the form of these hover sliders. But basically, in describing the algorithm of the paper, he intertwined pictures and dynamic infographics and prose. And really, I think that this is a model for the way things should be. So instead of trying to compress the author's ideas in their head to some very low bandwidth channel of a stream of text, you can have something like this, where you can really see what was in their head. And the potential of this form, I think, is to explain difficult concepts is unmatched and very, very much underused. So if you haven't heard of Brett Victor, you should check him out. Very, very cool guy. So I just wanted to start by giving a few motivational examples about what I consider to be high caliber info and data viz apps. The first one is called Cascade. This is, again, 5 years old. The New York Times, they built this interactive app to model conversations that stem from published articles. And basically what you're seeing here is a model of how people are talking about a specific article. And you can visualize all the conversations that stem from a single tweet over a certain amount of time. And you can see in 3D the conversational architecture that you can infer. It's much easier to do that in 3D. You can see the offshoots of the conversations and whatnot. I think this is a really, really cool app, and it's ahead of its time. The second example is something that I walk past every day on my way to work. The Internet Observatory at Akamai headquarters in Cambridge visualizes the entire internet. And what you're seeing here is a co-occurrence graph of carding sites from OpenDNS following the Target breach of 2014. You can see all these DNS queries over a few hours after the release of the data. So I have friends at this company called Athena Health, and they have a really strong visualization group. Basically, this shows an interplay of about roughly 10 million data points, transactions of patients' metadata during the course of only 24 hours. Each moving dot here is a single patient. And what's happening is when a patient seeks care, their dot moves from their home, which is orange, up there, to their doctor's office, which is purple, then to the referral networks, which is blue, and then finally converges to the payers for reimbursement in green. Again, this is all updated live from their data sources of all the PCPs around the country. And the final example, which is something I think looks really cool. So from the Center of Complex Network Research came this beautiful visualization where they generated a cosmic web. All that means is they were visualizing galactic superstructures by connecting discrete galaxies with their nearest neighbors to study cosmic inflation. And this is all, again, completely interactable, zoomable in a web app. So basically, all of these examples, they're really well-designed data viz. And if you compare these examples with what's currently possible in the Wolfram cloud, you'll see that we still have a long ways to go. My favorite piece of Wolfram code ever written was an idea that I shared with Vitaly, and he rewrote my idea much more elegantly, and it looks like this. So you're flying through a graph. All the dynamics have been optimized. So that's cool, but it freezes the front end. It's not deployable, the frame rates are low, it's not interactive, et cetera. So we really do have a long way to go to get to what the examples that I showed you before. So, and the sad thing is that it's really easy to do that kind of thing in Mathematica. It's just hard to deploy, and that's something that I was able to sort of overcome, the obstacle of deployment. And I want to talk to you about that. So, if you can't go with a ponderous plugin, like CDF, or a beta online system that it's just not there yet, well, what can you do to overcome these obstacles? I'm going to show you. So before we do that, I'm going to give you a little bit of a backstory on why I'm interested in any of this. So it's kind of a funny story. So I was contacted by a mathematician from the University of Chicago in the spring named Latzo Babai. His friends call him Lacey. So Lacey, he joined the University of Chicago in 1987, the computer science department. He's won the Gödel Prize and the Donald Knuth Prize, and he's a member of the National Academy of Sciences. So Lacey, he announced a really novel algorithm, his graph isomorphism algorithm, last year, November 10th. And how I got involved with this is, well, I was doing contract work for a technical magazine and helped with the publishing of an article on his algorithm. And they referred me to him. And that's how we met. And since then, I've helped him with a number of things, including developing lecture material for his world tour, specifically his talks at the Institute for Advanced Study and other educational initiatives around the world. So I wouldn't dare try to go through his 90-minute lectures slides that we've built in the remaining 15 minutes, but I would definitely encourage you to get his article or watch the talks. So, quick summary of the result. You have to understand what isomorphism is first. You all know what graphs are. Computer scientists use the word graph to refer to a network of nodes with edges connecting them. And GI, graph isomorphism, it's a problem, a decision problem that's really easy to state but tricky to solve. It just asks, are two graphs really identical? Are they really the same graph in disguise? And what does that mean? Formally, it means that if there's a one-to-one correspondence between their nodes such that it preserves the way the nodes are connected. And here you have an example of a Peterson graph. These are all the Peterson graph. They're just different embeddings. So certain pattern recognition problems are readily mapped onto graph or subgraph isomorphism detection. Like the structure of chemicals, if you're looking up, trying to identify some molecules in a structure database, you're looking for a particular functional group. That's just an instance of subgraph isomorphism. So this is a very useful thing to be able to do. And to understand the statement of his result, the one buzzword is quasi-polynomial time. And you can ask Wolfram Alpha about that. So all quasi-polynomial time means is that it means that if you have a graph with n nodes, that the runtime of the algorithm is comparable to n raised to, well, not a constant that would be polynomial, but to a power that grows slowly. That's the idea. And the algorithm he introduced, quasi-polynomial time algorithm, is vastly more efficient than what was known before. The best previous algorithm, which has held the record for 30 years, was due to a professor emeritus at the University of Oregon named Eugene Lux. And so last year he improved the bound, and this is really a big result in computational complexity theory, and I'll explain why. Well, let's just say in practice, the best known isomorphism testing algorithm is Naughty, which is inside Mathematica. Sadly, it's not implemented fully. The generalized fine graph isomorphism function isn't there, so it doesn't work on, say, multigraphs. But I would refer you to iGraph. So iGraph is one of the most complete open source graph manipulation libraries, and it can do this. And there's a beautiful library link code that interfaces with it. It supports multi-graph isomorphism testing directly, motifs, minimum feedback arc sets, random rewriting, all this stuff. It's really good. So what did his result do? Well, it didn't prove that isomorphism is in P, but it did. You could say it put GI in the greater metropolitan area of P. So, and P is just a set of problems that can be solved efficiently. I'm getting a pop-up here. Okay, cool. So P versus NP, right? It's a big unsolved problem, and asks, are all problems in NP complete? Do they have polynomial time algorithms? It doesn't really have ramifications for it, but it is really interesting. If you know about these things, it could disprove the exponential time hypothesis and some other interesting things in approximation theory, or in approximation theory. But I'll leave you to the details because it takes a long time. It's really heavy. So rather than talk about that, I want to talk about how we built his lecture material. So the first thing that you'd want to do when setting up tours for your deck for going around the world, giving these talks, is you want to have interactivity, right? So you're an academic, you have Beamer, you want to export frames and import them as an animation. So that's the obvious first thing to do, is to generate animations showing how various embeddings transform and translate between one another. And you can do that really simply in Mathematica, and it's fun. So for instance, a Pappas graph, what you want to do is you want to generate all these frames, and you want to do it in parallel, and you want to do it with internal bags, and do it in a resumable way with local symbols, so that, because things are going to crash a lot. And the frame rates are kind of crappy, but you can improve them. No, don't use list animate. This is trouble. Many times if you try to import, export GIFs, you will crash the kernel. So you can enhance them with a little bit of dynamic trickery, and you can make them as smooth. You can make them upwards of 50 frames, 60 frames a second, and that's lovely. But when you have many of them, then it's not lovely. Then everything comes to a grinding halt. And the same for large graphs. Let's see. So for 2, it can handle it. For anything more than 2, basically the front end just grinds to a halt. So that's an issue. So it's going to kill that. And the same thing for large graphs. Everything just grinds to a halt. So this brings me to the main point, the main thrust of the talk, which is how do you deploy interactive infographics that are beautiful and world-class? Well, you need to go beyond Mathematica to interface with third-party libraries in various languages. And this is just a slide about all the issues. So I tried. The first thing I tried was using the cloud, and there's issues with stability and frame rates there. But what you can do is you can use, for these Mathematica symbols, you can use these open source solutions. So for graph, you can use something called Sigma. For graphics, you use D3. For graphics 3D, you want to use Three.js. And for cloud deploy, instead of that, you can wrap everything up into a node server and deploy it with React Native. And so I'm going to show you demos of all these things. Yeah, unless you want to print it to a PDF, which probably won't work, or save it as HTML with tooltips, which won't work, or what have you. So the first example is using Sigma. So you can get frame rates that are insane. So basically, I exported the entire graph data inventory of all graphs, and they're all running smoothly in a single web page that you can open up on a browser. So Sigma is a wonderful library. It's plug and play. It's very easy to draw force-directed graphs. It has a force-to atlas algorithm, like the one in Gephi, which is another great tool for doing graph stuff. It's significantly faster than D3, especially with the if you use WebGL. So it's fun to look at. So the next example was I wanted to take basically any 3D graphics, 2D graphics, and graph objects, and basically transpile them, right? So rewrite the source in a different language, maintaining all of the graphics properties of these objects and the dynamics, and you can actually do it. And it's not that hard. And you can get results that are just really super smooth, because the JavaScript can go down to bare metal now with OpenGL. So you can achieve speeds of interactivity that are way beyond anything possible in a CDF. Yes?
Advocating that Wolfram create link, JavaScript link, that you can move graphs over the graph object. Not anything Wolfram proprietary, but the graph object, so that you can exploit Node.js or Three.js.
Yes.
Node. Is that kind of your argument?
Well, so that's what I did, and I'm putting it on GitHub, GitLabs, and everything. No, absolutely. But it already does it, right? With APIs, you can generate JavaScript to do stuff. But JavaScript has limitations, and I just wanted to show you something. So basically, if you want to do something a little bit more complicated, and you want to use some hardcore graph algorithms, you might hit some walls. So for instance, this is another beautiful demonstration that I think is lovely by Stan Wagon. So what this looks for, Hamiltonian paths. Basically, you start on a black and you end on a white, and hitting every cell in between. And in this example, he's using some powerful graph algorithms, or it might just be caching, but you get the point. You could be using these graph algorithms that aren't necessarily, when I rewrote it in JavaScript, available. Now, there is a, what is it called? I forget what the actual name of it is, but there's some guy who has a quote that says, anything that can be written in JavaScript will be. And it might be for Mathematica, that might be true, I don't know. But you can see, look how slow it is it's going as computing, millions of these paths every second, but it's not doing it in a smart way, right? If I had access to some of the higher level operators in Mathematica, I could do this much faster. And being able to export these things would be great. And that's why I'm so excited about the LLVM project. That was always my 5-year hope for Mathematica, and it seems like it's coming to fruition. And Tom Wickham-Jones promised me that Graph will be there as one of the compilable objects, which would be really, really cool. And the final example that I have here, yes?
People like Jan Pritschko and John Casey have been working really hard to basically get HTML version of CDF to support as much as possible on the client side. So obviously, whatever Manipulate can do will not available right away, but there are a bunch of things that are simpler, which have been completely translated into JavaScript, so you can get a smooth Manipulate, for example, for certain examples. So
right.
I don't know, if you haven't seen those talks, go.
Yeah. Yeah, and the original hope was, with Luke Bartlett, we tried to do in Scriptum, that path of really compiling the front end to JavaScript, and it just failed. I didn't think it should, and it's possible to do. So the last library that I want to talk about is Three.js, and you mentioned CDF, but really a plugin is never going to work, right? No one will actually use 500 megabit plugin, so this is a dead end. So Three.js, what is it? Well, it's a way to export. I've written a way to export graphic primitives into a WebGL wrapper written in JavaScript. And what does it look like? Well, I had a really sexy demo, but I'm not going to be able to show it to you because version 11.1 broke all neural networks. So suffice to say, I had this beautiful demo where you take LeNet, GoogleNet, and you visualize what the outputs are of each neuron. And you can dynamically draw something like a character. It's trained on MNIST. It'll show you, it'll propagate through and it'll show you the neural responses from all the layers. So I exported it. You can export any net graph into a JSON object. And then you can use things like synapse.js or any other convnet running on JavaScript library, and many of which exist. One was written by Karpathy. And you can try it. So let's see. What does one look like? Well, here's the input field. Now, as we zoom through, you can actually inspect every single connection and every single computation in the entire network. And this is all running at super high frame rates, and it's just super fun to play with. And so this is really the future, I think, for all deployments. The future isn't CDF. The future isn't necessarily a private cloud, although I'm excited to see what that can be. But really, I want to get back to Mathematica's strength is a prototyping language. And if we build in links from the kernel to external things like Python, like Sigma, like JavaScript, like Nodebox, like Gephi, like Nginx, if we could serve web pages for real, somehow, this is sort of like war cry and feature request. Please make exporting code easy, and that's in process. So I just wanted to give a summary because I only have a minute left. So I gave some examples, and hopefully they motivated you to think of what's possible in terms of deploying beautiful visuals from Mathematica to the web. That's what I'm doing for Lacey. Yeah, so that's sort of the summary, right? We need JavaScript integration and/or enhanced exportability for pieces of code. So thank you for listening. I have the packages that I use, for instance, like to view video in Mathematica and other things. I'll be releasing all of them. And if you're interested in computer vision, then you should come talk to me, and I can get you an API key so you can use Ditto's tech. But that's everything. So thank you very much.